So I'm going to be attempting to solve this set of simultaneous equations using the matrices and the determinant and adjacency method. I really said attempted because I just did this again with an easier matrix, and I must have made an arithmetical error because it's so easy to make one error and it messes it all up. But I'm going to try be very careful this time. So how do we go about solving a set of equations like this? We can map them to matrices. So we can map the coefficients of x in the first column 2, 3, 5. The coefficients of y are 3, 6, and 4, and the coefficients of z are 5, 15, and 10. What's nice about these is there's no negatives in it. And then we can think of this about multiplying by x, y, and z, and you can say this is equal to 21, 51, 37. These numbers here are very not nice. The reason why this works is, so let me just, I'll use this colour, get it a bit wider, 1 second. Okay, never mind, let's just use this. So 2 maps with the x, so doing multiplication this will be 2x. The 3 maps with the y, 3y, and the 5 maps with the z, plus 5z, and on the first row this equals the 21. So this is how they map the matrix to this simultaneous equation. These two things are equivalent, and we have to solve this matrix equation now instead of solving the equation by just manipulating the equations. How can you solve an equation like this? If we let let's let v be the vector of x, y, z, and let w be the vector of 21, 51, 37, and a be this matrix here. We're trying to solve the following matrix equation. We're trying to solve equals w. So you can think of this a as being a transformation on the vector v, and it transforms into w. We can undo this transformation by doing the inverse of the transformation. Just like if you have a transformation which maps one point to there, if you do the inverse, it will map it back like this. So that's exactly what we're trying to do. We're going to try find the inverse transformation of A, apply it on the transformed vector W to get back to V. V. So basically, if we go like this, multiply both sides by the inverse, we get the following. The A's and A's combine and form the identity matrix, and that is equal to A minus 1. So basically, the vector which we're looking for, which is x, y, z, the v vector, which is the solutions, is equal to the inverse matrices times by 21, 51, and 37. I hope that makes sense, but we're going to swiftly try and move on and attempt at finding the inverse, because that's the real hard part. So, how do you find an inverse of a matrix? We're going to be following the adjugate determinant method. So this basically says if you've got a matrix M inverse equals the adjugate of M over the determinant of M. This may commonly, the adjugate is often like, it's the matrix of minus method, that's how you go about finding it. It means the exact same thing. So let's attempt. So first of all, we need to find the determinant because that's easy. I say it's easy, I'll probably go mess it up. So I'm just going to write A equals down here 2, 3, 5, 3, 6, 15, and 5, 4, 10. So let's go down here and have a go. So the determinant of A is going to be equal to, we can pick any row or column, and 2, 3, 5, 2, 3. I'm just going to pick this one here for no reason. 2 times 60 minus 15 times 4, which is 60. Nice, that's 0. I very much like that. 3 times, so that's going to be 30 minus 5 times 15, so 30 minus 5 times 15, that's going to be 50 plus 25, which is 75. And plus the final matrix 5 lots of, and then that's going to be, 12 minus 30. So 5 lots of 12 minus 30. That's going to be 0. Minus 3 lots of 30 minus 75, that is minus 45. And 5 lots of 12 minus 30, that's going to be 5 lots of minus 18. 3 times 45 plus 5, 3 times 45, that's going to be positive. That's going to be 120 plus 15 is 135, minus the 18 times 5. 18 times 5 is what? So that's going to be 50 plus 40 is 90, so 135 minus 90 is 145. I believe the determinant of A is 45. So we're going to take this knowledge and write this over here just for usefulness. Determinant of A equals 45, and we're going to carry on trying to find the matrix of minors and the adjugate. So let's carry on. So let's go like this. Considering the top left item, 60 minus 60, so it's going to be 0. 30 minus, I'm just going to use my calculators for this because I cannot be bothered to make up a arithmetical error. 30, that's going to be minus 45. This is going to be 12 minus 30 is minus 18. Minus 18, I've already done these before with the calculation of the determinant. So this is going to be 30 minus 20, this one is 10, I can do that on my head. This middle one is going to be 20 minus 25, so that's going to be minus 5. I can do these in my head. What's this one? It's going to be 8 minus 15 minus 7. This one's going to be a bit harder. 3 times 15 is 45, minus 30, this one's going to be 15. This bottom here is 4, this would be 30 minus 3 times 5 is 15, so 30 minus 15 is 15, and this last one is going to be 12 minus 9 is 3. Apart from these ones here, they're all multiples of 5, so don't know if that means anything, but it's nice. So this is your matrix of minors, is sometimes called, and we still need to do some stuff. We need to apply the following, like this. This goes minus here, this goes plus, plus, minus, and that's a minus 10 there. So we have minus on all of these. And now we're going to flip this, we're going to transpose this matrix. So the main diagonal is invariant. 45 goes down here. Minus 10 goes here. Minus 18 goes here. 7 goes here. Minus 15 goes here. And 15 goes here. So let me check. 15, 15. 7, 3, 45. Minus 10, I think that's right, and we did multiply this by 1 over 45. So 1 over 45, and this looks very gross. 0, 10, 15, 45, minus 5, minus 15, minus 18, 7, and 3. I say this looks gross, 45 cancels quite nice, and all the others do, but there's a 7 in that, 7 45ths. That is not nice. So this is 0. I'm just going to leave it in 45ths because it makes it easy for me. 15 over 45ths. 45 over 45. Minus 5 over 45. Minus 15 over 45. Minus 18 over 45. 7 over 45 and 3 over 45. We then multiply this by our original solutions, which are 21, 51 and 37. 21, 51, 37. I really need to calculate for this because I have no chance. 51 times minus 10 plus 15 times 37. Oh, this is showing good niceness. This gives 45 over 45. So I didn't think that was going to cancel out and be so nice, but it does. Okay, so the next one, 45 times 51 minus 5. No, sorry. 45 times 21 minus 5 times 51 minus 15 times 37. 135, yes, very nice numbers. 135 over 45. And when I mean they're very nice numbers, I mean they're divisible by 45. Let's see if we can get a nice number for the last one. So 21, so minus 18 times 21 plus 7 times 51 plus 3 times 37. 90, beautiful numbers. If they're wrong, I will be very sad. So we've got our solutions are x is 1, y is 3, and z is 2. Let's just plug them back into the first equation to check. 2 plus 9 is 11, plus 10 is 21. That works. 3 plus 18 is 21, plus 30 is 51. The last equation, 5 plus 12 is 17, plus 20 is 37. So those are our solutions. Double checked. Back in. X is 1, y is 3, and z is 2. Very nice.